This is the first video in Unit 17, the acid-base unit. This video will cover the Arrhenius definition of acids and bases, as well as neutralization reactions. By the end of this video, you will have observed some common properties of acids and bases. You should be able to distinguish between Arrhenius acids and Arrhenius bases. You should be able to write neutralization reactions, and you should be able to predict the products of a neutralization reaction. Let's start by looking at some properties of acids. So if you've ever tasted a lemon, you might know that the citric acid in the lemon is what causes it to taste sour. Of course, we won't be tasting anything in lab, so in lab you'll just have to take my word for it. They can also sting your skin if they come in contact with bare skin, so we'll be wearing gloves in lab during the acid-base unit. They also react vigorously with metals to form hydrogen gas. This is something we'll be observing in lab. And they conduct electricity when they're dissolved in solution, so we can call them electrolytes. Some everyday examples include citric acid in lemons, as I mentioned, and acetic acid in vinegar. Moving on to some properties of bases. Bases generally taste bitter. You may have noticed bitter greens that you eat. They often are highly basic. They also feel slippery on your skin. Again, we'll be wearing gloves in lab, so you probably won't experience this. And they do not react with metals. They do, however, conduct electricity, so they are also electrolytes. Some everyday examples include drain cleaner, like the one you see at the right, and hand soap. So what is it that makes an acid and a base a base? Well, there's actually several different definitions. The one we're looking at in this video, however, is the Arrhenius definition of acids and bases. So this handsome fellow right down here, that's Arrhenius. And he tells us that Arrhenius acids are substances that produce H+ ions in solution. So it's this H+ that's going to be crucial. So you might recall, if you dissolve HCl in water, it dissociates to give you H+ ions and Cl- ions. Likewise, if you dissolve H2SO4, sulfuric acid, in water, it dissociates to give you two H+ ions and an SO4 2- ion. It's these H+ ions that make sulfuric acid and hydrochloric acid Arrhenius acids. Turning now to Arrhenius bases. Arrhenius bases are substances that produce OH- ions in solution. For example, if we dissolve NaOH in water, you might remember that you get sodium ions and OH- ions, or hydroxide ions. Likewise, if we dissolve calcium hydroxide in water, it will dissociate to form calcium ions and two hydroxide ions. In this case, it's the OH- ions that make sodium hydroxide and calcium hydroxide Arrhenius bases. Here we see a list of some common Arrhenius acids and Arrhenius bases. Notice in every case the Arrhenius acids contain H+ ions. It may be 1, it may be 2, it may be 3. And in each case, the Arrhenius bases contain a hydroxide or an OH- ion. So what happens when you combine an Arrhenius acid with an Arrhenius base? You get a neutralization reaction. A neutralization reaction is an acid-base reaction where just enough strong base is added to completely react with a strong acid. At this point, the moles of acid will be equal to the moles of base. Or, if you prefer, the concentration of H+ will be equal to the concentration of OH-. A simple schematic for this kind of reaction is that a strong acid plus a strong base yields a salt and water. Remember now, in this scenario, a salt means any ionic compound, not just NaCl, so any combination of two ions. Also note that neutral solutions have a pH equal to 7. We'll be talking much more about pH a little bit later, but for right now it's just important to know that the pH of a neutral solution is 7. Let's take a look at a really typical example for a neutralization reaction. Neutralization reactions are essentially a special type of double replacement reaction. So in this reaction, the strong acid, HCl, is reacting with the strong base, NaOH. Like all double replacement reactions, the positive ions switch places. This gives us the new salt, NaCl, as well as HOH, better known as H2O, or water. Let's practice writing some neutralization reactions. In the first example, let's take the strong acid, HCl, and combine it with the strong base, potassium hydroxide, or KOH. Again, our positive ions will switch places, and we'll end up with the salt, KCl, and HOH, or water. Notice that water will always be a product of our neutralization reactions. To take another example, let's take nitric acid, HNO3, and combine it with sodium hydroxide, NaOH. Again, our positive ions will switch places to give us the salt, NaNO3, and again, H2O. Let's take a look at a slightly more complex example. In this example, we're going to combine sulfuric acid, H2SO4, with lithium hydroxide. Notice in this case we have two hydrogen ions present. Again, the positive ions will switch places. Remember to take into account the charge of each ion, so we've got an Li plus ion and an SO4 2 minus ion forming our salt. By the crisscross method, this gives us Li2SO4. So our salt in this case is Li2SO4, and of course our other product is always water. Unlike the ones we looked at before, this equation is not balanced as written, so we're going to have to balance this equation. Notice we have two lithiums on this side and only one on this side, so I'm going to put a 2 in front of the LiOH to balance the lithiums. This now gives us 2 hydrogens plus another 2 hydrogens on this side, which is 4, whereas we only have 2 on this side. So I'm going to put a 2 in front of the H2O. This should balance our equation for us, but be sure to double check. Finally, let's take a look at one last example. In this example, we're going to be combining the strong acid, HCl, with the strong base, calcium hydroxide. Notice in this case we have 2 OH minus ions. Once again, our positive ions switch places. We end up with a salt formed with calcium 2 plus and Cl minus. Again, by the crisscross method, our salt will be CaCl2. So our salt product is CaCl2, and our other product is water. Again, we're going to have to balance the equation since it's not balanced as written. Notice we have 2 chlorines on this side and only 1 on this side, so I'm going to put a 2 in front of the HCl. This will now give me a total of 4 hydrogens on this side, whereas I only have 2 on this side, so again I'm going to add a 2, and this should balance our equation. Let's quickly review our goals for this video. So we observed some common properties of acids and bases. We discussed the fact that acids generally taste sour, whereas bases taste bitter. And we also talked about the fact that they are both electrolytes. They both conduct electricity in water. We also talked about how to distinguish between Arrhenius acids and Arrhenius bases. Recall that Arrhenius acids produce H plus in water, whereas Arrhenius bases produce OH minus in water. We also learned how to write neutralization reactions as well as predict the products of a neutralization reaction. Recall that a neutralization reaction involves a strong acid combining with a strong base to form a salt and water. For example, HCl combines with NaOH to yield NaCl and H2O.